Solving more complex problems in heat transfer requires formulation of the heat diffusion equation. This is done by conducting an energy balance on a differential volume, which has dimensions dx, dy, and dz. There's a heat flux qx double prime entering this differential volume through the face defined by dz and dy, and a flux qx plus dx double prime leaving through that opposite face. We define similar quantities in the y and z directions, and there is also a term q dot gen, which defines the heat generation within this volume. It has units of watts per meter cubed. We can now write an energy balance, which has units of joules per second for each term. This has a heat current coming in, Q sub in, a heat current coming out, Q sub out, as well as a generation term, which involves q dot gen times dx, dy, dz. We have to multiply q dot gen by dx, dy, dz in order to get the units right, because it is a volumetric generation term. This is all then set equal to dq dt, the rate of change of the energy content of this volume. Then we make use of the definition of the heat capacity, that Q equals m times Cp times a temperature that is referenced to a reference temperature. The mass of this volume, m, is the density times its volume, and that volume can be expressed in differential terms, dx times dy times dz. We plug in with this, and we end up with this equation. And we then rewrite the heat currents, these terms Q in and Q out, based on heat fluxes. So each of these terms can be decomposed and then reorganized along the dimensions of interest in the x, y, and z directions. We're taking fluxes and multiplying those times the area through which they occur, such that we can substitute for a heat current. We then divide through by dx, dy, dz, and we take the limit as dx, dy, and dz go to 0, obtaining this differential equation. And then we can apply Fourier's law. This allows us to plug in for q double prime in each dimension, such that the equation now depends on only temperature. This is the heat diffusion equation, which will be critical for a wide range of heat transfer problems that we will solve. So we can take the heat diffusion equation that we just derived, and we can now apply a simplifying assumption to it, that K is spatially invariant, that Kx equals Ky equals Kz. This is an isotropic material, and we now get this equation shown here. We can also recognize the Laplacian operator, del squared, as well as the thermal diffusivity. This is alpha, which is defined as K over rho Cp, and we end up with an even simpler equation now.